So, so thank you for coming late with me today. We had this religious holiday, Muslim holiday. It's called it Eid. So I was busy with that. So anyway, we'll get started. You guys can see my slide.
Yes.
All right. Okay. Very good. So we'll continue now in module 3, and a couple of announcements which I already sent. I know that in that email I had a couple of misspellings. But this is module 3 that we are in. And for the KPR presentations, the video presentation, I have made a discussion board where you can upload the video. Use the link in there. There is a special link in the discussion board which you can click to upload the video. And then I've asked every student to comment on each other. I think 3 times at 3 places. For the GRP, I will be opening a discussion board so you guys can talk to each other and share your, I think maybe mini resume so you know each other's background if you don't know about each other already. So you can form teams. Some of you may already know each other. You already are ready to make a team, but that's on the administrative side on the program. So I delayed the KPR key paper review submission, so that has delayed everything now. So, but we still will be able to catch up with all of the things that we plan to do. All right, so that's why I delayed the giving out the module 3 also. So, but module 3 we are focusing on the language or vocabulary related to manufacturing of nanomaterials or nano devices. We'll discuss next generation lithography and specialized fabrication, and then we'll go into 1D, 2D, 3D nanostructure. We'll also talk about 0D nanomaterials as well, which is quantum dots or nanoparticles. Especially quantum dots is what we call as 0-dimensional. So let me get some feedback. So is the course on the right pace? Is it too fast, too slow, too much material, too less material? What do you feel?
I would say it's fine. I mean, we're on time. We're keeping up on time. So I would say that it's fine. It's fine by me.
Okay, Beto, you have taken course in class for me also, and now you're doing this. So do you think
This is my third class online. I take physics. The lecture was online, but the lab will has to be on lab. I'm taking another class which lasts 10 weeks, which is called manufacturing engineering right now. So I'm taking basically 2 classes
okay?
right now. I'm taking that class and then this class.
So how's
So
the material
it's
for this course? You have taken class from me, like face to face also, and now you're taking online. So
yes.
is this the
I
same?
mean, it's pretty much basically what we already saw. I don't know some of the classes or masters, but it's super similar to another class I take before, besides your class, which is Introduction to Nanotechnology. But this is super familiar. Some keywords that kind of confused, like, oh, what's going on here? I had to Google what is the meaning of that word because it's kind of new one. But so far, so good.
Very good.
Yeah. Well, before we continue, are you gonna set the time Friday fight time as we're gonna go back to 11 a.m.?
No, we'll do 11, but this is asynchronous class, so there's no need to do in real time, but I like to do it in real time. So if somebody has any questions or clarification, or I like to have this
Because
opportunity.
if because I'm not morning person, to be honest. I like this time. 5 o'clock is super neat for me.
We
And
will
somebody
we can do
so
we can do a poll in the class and see if they prefer the morning or the evening, right?
yes, and I have a sorry, I have a question for the KPR because
Right. Good.
if I'm understanding the word correct, it's supposed to be a summary of the paper, if I'm not mistaken, and then we had to put place on that paper.
There is there were
So
specific requirements for the KPR. You had to, of course, identify. You have to talk about it. Then you have to write 2 key impacts it had. You had to identify maybe one challenge. So there are specific things you had to do about it. But yeah,
Yes.
overall, it's just a review of.
So the thing is, I make a terrible mistake. I know it's already late, but no, I'm gonna have to deal with that. It's
We can
because I mix the.
we can discuss your personal specific problem away from this joint session. I don't want to discuss individual students' problems because this is being recorded and I'll be posting on YouTube. So we can talk about it one-on-one.
Okay, okay,
Right?
sounds perfect. Sounds good. Okay, sounds good.
All right, so let's continue on lithography. A little bit
Okay,
on,
that's okay.
we saw that we could make a window in photoresist and transfer that into silicon dioxide. Now, when you do that, what do we make? How do we make devices? So if we think about a simple device, which is a PN junction or what you call as diode, right? So when you
Yeah,
do diode forward bias, what does it do?
it
Conduct
rectifies.
currents.
When you put a diode in forward bias, what does it do? So Isaac, you said it's rectification that it does, right?
Yeah, yeah.
Yeah,
Right. In forward bias, it conducts, and when you put in reverse bias, it does
It
not.
does.
Right. It
It
does.
doesn't. Yeah.
Yeah.
It conducts currents, and when it's forward bias, it doesn't.
Right. So we look at the fundamental design or how it is made. So you have to make one area P-type, and the next area to it would be N-type, right?
Mm-hmm.
Then we would make connection with P and N electrode with small metal electrode. So this is how, when you, continuing from last time, when you had made the window in silicon dioxide, then we do the doping and you make a P-type region there. And then if you take it next step, then we would grow oxide again, and then we open the window next to that area. And if that next region would be, I'm just going to use the to draw thing. So then you would make maybe window here, and you would make next region to be N-type, right? And hence you will make a diode. So that's a very simple explanation of what we do when we do photolithography, right? So now I'm showing that we can grow silicon dioxide, and then we can do photoresist coating again. Then now this is showing how we would make electrode connection with P-type side. So then we would put another mask and do lithography again. Now we are making a smaller window in silicon dioxide. In that window, then we can put the metal down, and that metal can make it connection with that positive terminal of diode, right? So we talk about circuits. We just talk about the positive and negative side, forward bias and negative or reverse bias. But in actually, this is how it would be made. Connection with P type. And then next window would be N type, and we will isolate, and then we would continue with that, right? So then we can remove aluminum from everywhere and just have the aluminum exactly where the P type part is there. And so this would complete one half of diode fabrication, right? So in photolithography, we said we use or what we also call it optical lithography. So we use UV light. But UV light, there is a very fundamental relationship of the wavelengths of the light with how small a feature we can make. But directly, if you think about it, the smaller the wavelength, the smaller the feature we can make. And there are some equations which come into that. We will not go into those equations, but take me on the face value that we can make the smaller feature if you use smaller wavelengths. So over many years, then we have been trying to push the wavelength of the light used. So then from UV, then you go into deep UV. So krypton fluoride or argon fluoride or even fluoride lamps have been used, which can create that wavelength, which is very small. But there are other issues that come with that, because if you make the wavelength too small, the energy of that light goes really high. And if you don't know, we have a simple relationship of energy with wavelength, which is E equals hc over lambda. I don't know how to make that. I'll just write the whole thing lambda. So when you say lambda, which means if you are keep on pushing the wavelength down, the energy keeps on going up, right? Because it's an inverse relationship. If that happens, then we have issue with the optics, the lenses that we would use. Those lenses would start becoming dense because the energy of the light would start messing with the material itself. So we cannot then use those optical lenses. We have to then look for expensive lenses or specialized lenses, and that adds to the whole the cost of the material, cost of the equipment. There is another issue when you may be making too small, but then the problem becomes that how close can you put next thing to it? Remember, there was this thing called pitch. We talked about it, pitch, when we were talking about technology node. If you make them too small, then it becomes a problem. The waves starting interfering with each other. So you cannot make two small features very close to each other. So then what's the big deal if you cannot make too many? You can make them small, but you cannot fit too many of them. So hence there have been issues where we have been getting into other ways of how do we do lithography. So there is now, I say there is a wish list now of what we want to do. We want to have this plot shows that it's called Tennant's law. So what is happening here is it's just showing that we want to make things smaller, resolution. We want to make them smaller, so it should go down, right? So, but if you make things smaller, the throughput also goes down. Now, what does it mean if the throughput of your manufacturing goes down? For example, if you have a factory and you make 1,000 pieces one day, and now if you want to make them smaller and you can only make 100 pieces in one day. So what happens to it? Cost goes up. You cannot manufacture fast enough, right? Manufacturing cost goes up. So we have the equipment and we have been trying to push to the lower left. So we start here. We'll talk about E-beam lithography and all these things. We have different ways how we use E-beam lithography or what is called the atomic force microscopy. We'll discuss what is E-beam lithography. Right now, I'm just taking a transition from optical lithography that we want to make things smaller, but we don't want to compromise of how fast we make those things. And that's what Tennant's law basically explains, that dimension and throughput are related. You make dimension small, throughput goes high. Throughput goes down as well. Does it make sense? So ideally, you want to be on the lower right side of this chart, which is where it's shown with an X. And this means what is written on the left side, that we want to make the dimension small, but we also want to keep the throughput high, right? So that's the trade-off. That's the problem that the industry is facing. And this is wish list that we want to move things to the right and lower side. We want to make things smaller, but we also want to make these things quickly, so we don't lose on the cost. So,
sure.
Yeah.
So as we may make more transistor and compact in this
we want to make
area
transistors. So we want to compact more transistors. But if
an example for a power devices, they don't mention something about the heat exchange between them doesn't affect them as well.
Right. Yeah. That's now another factor now. That's not related to manufacturing challenge. That's not related to operation challenge. That Yes, we can make million transistors or billion transistors, but can you remove the heat they would generate
Mm.
fast enough for them to be viable? Then this becomes a packaging issue.
Oh, okay, okay. That's different stuff. Okay, I thought
Right,
that
right,
was related to this.
right. So, but the packaging issue or how fast can you remove the heat also then feeds back to the manufacturing, what we are talking about. That do you want to make, you want to change material that is better in heat transfer, right? So you can, whatever heat you make, you can quickly move out. So it's a very important thing that what you have highlighted, that it's not always just how fast or how many you make. We also have to make decision of what material we are using and what configuration we are using. Are we making multi-levels now? So the electrodes are not just running in X, Y, they also have to run now in Z direction also.
Mm.
So now when you have multi-stack, then you remove the heat from the bottom or the top or the side. How do we remove the maximum heat from that machine? So that all will feed back to the design of the chip, which will result into changing what kind of lithography we use, right? We may not require to make something very small. So, but you're right, these things, but they are packaging issue or testing issues which would result. So here we are just focusing on lithography, that what are the limitations which are imposed by the system of lithography, where a VLSI designer has made the layout. Now we have to fabricate the layout, and how do we fabricate that? Right. So now, what are a few metrics then which define our lithography or fabrication process overall? It's the throughput. We want to make many of them together, same speed as we are making before, while we make them smaller. Second thing here given is resolution. Resolution has three things to it. We want to make them small, right? But we want to be able to distinguish one feature from the next feature. Hi, Krista. Sorry, we started already at 5 o'clock. Thanks for adjusting your schedule with me.
Sorry.
Yeah. So we are discussing lithography, optical lithography. I shared a lecture with you guys, and we talked about it last week. So we continue because lithography leads us to next generation lithography. And we are talking about lithography is the process where we transfer the design from a VLSI concept to an actual fabrication using masks and light projection and material coating and all that.
Okay.
All right, so another metrics for lithography or transferring is that we want to maintain quality so we don't have too much defect in our fabrication. You know, when you keep on making things smaller, there are more chances of defects, of maybe the feature not coming out right, maybe the feature are merged together, so two devices become bad. So we want to maintain the quality. Now, when you are talking about deep UV and or making specialized smaller wavelength things, we have to invest in upgrading that equipment. We need to then put effort in training new people. Now, when you make features too small, we definitely cannot have people making those assessments and alignments. So we want to automate these things. And now when you keep on making things smaller and smaller, we are reaching the quantum limits. We are basically reaching the atomic scale. When we say quantum limits, yep, looking at the movies, sometimes I cringe on the way the movies talk about quantum phenomena. But quantum is simply that when you get to the atomic level, now if we start messing with how electrons are moving around those atoms, that's what we call quantum limits, because now we would be changing the behavior of an electron, bunch of electrons, the whole network of electrons. When that's happening, which means the devices may not be operating how we know them to operate at a bigger level. But that's what we say physical and quantum limits. Alignment, important issue that if you make one layer of design, like in a diode PN junction, you have made the P area, then you have to put the N area very next to it. So you have to align the next level with the whatever already made. That's also where we want to have to maintain precise alignment going from one step to the other. This is becoming a little bit specialized, what we are discussing now. You may have questions, I can understand, but this is a major step going understanding the lithography aspect of nanofabrication, because this is at the heart of things, how we make things smaller. Now, you make things nanoscale, we want to parallelize and make many things together, which means that ideally we want to use the similar thing where you have a mask, you have the wafer, silicon wafer, you can just shine the light, the whole thing gets flooded and you can transfer all the pattern on the surface. But that becomes a problem because now if we talk about electron beams or ion beams, now we have to take one beam and write one feature at a time, which reduces the throughput. That's number two. So when we are talking about alignment, we're talking about features 10 nanometer or smaller than that. Remember, there is we have now 14 nanometer devices, which means the half length, half pitch from one device to next one is 14 nanometers. So they're so close. You mess up 1 nanometer in alignment, the whole chip will go defective. So this is something when you say we want to push things, but we want to maintain some relationship with how we are doing things before. Right? So what are some next generation lithography systems? It's a big list. We'll talk about 2-3 of them in detail, which are used in the industry. But going from UV, remember we are talking about we want to push the lambda down. We want to push the wavelength of the light down. We go to deep UV, we go to extreme UV. And then from smaller than extreme UV is X-rays. That's how it says, extreme UV, where you can make things smaller. But then you go to X-rays. Now X-rays have problem. X-rays can penetrate through, X-rays have so much energy, they can penetrate through hard material. They can penetrate through our body. So it becomes difficult to have this idea of masks because they can go through everything. So that's why we have moved on to where we say, okay, instead of using light and flooding, we take electron beam and we start writing it. It's very interesting. If you think about writing, we know pens, right? We know pen, there is a tip, there's ink inside, and we write with it. We write serially. Think about it, right? We write serially. We start from one side, we don't have a stamp. Now when we talk about stamp, how does a stamp write? Parallelly, right? I do have my professional engineering stamp. PE stamp. How does it write? Parallelly. That's what UV or optical lithography was doing. But now I say, no, I want to take E-beam, I want to write. And the reason is because, okay, Beto figured out how to change his background.
Yeah.
That's the big thing. Beto, you have masters of electrical engineering. You have to have people working for you doing these small things for you. It's okay. Pulling your leg, man. All right. So that's when we go on the left-hand side, we are getting into what you call electron beam. One beam. Now, question is, where do we get those electron beams from? How do we get electron beam? So there is these are things called electron guns. They're not guns. They have nothing similar to guns, but what they have is you have this source material, right? Some element, you pump energy into it, you turn it on, and electrons would emit. So you want to condense those electrons, and then you have those electromagnetic coils around. So you narrow those electrons that are coming into very tight beam, right? So that tight beam, then you put, now across that gun, you have put
This is similar to the CRT, the old TV ones.
exactly. You got
Oh,
it.
it's the same thing. It's the same thing.
Exactly. The cathode ray tube.
Yeah, the cathode ray.
They're
Yes.
emitting light out of the screen towards you people, right?
Yeah,
Not
to excite phosphorus, something inside.
exactly. But not everybody knows the principle of CRT. So we have to.
Oh, okay, okay.
So you're creating electrons, but electrons can go anywhere. So we put the electromagnetic coils so we can electronically control them and put them into a form where they create a narrow beam, and then you have the opening, and they come out in the form of a very tightly focused beam. And we have a whole big cylinder under very high vacuum. So we don't want those electrons to deflect off of any air particles. So they go shoot straight to wherever we want them to shoot. On the surface, we have a coating of material. Here we call it E-beam resist. Similar like optical photoresist, a material that would undergo chemical changes when electron beam strikes it. So when you put it into developer, into chemical, it gets washed from wherever the beam did not strike or wherever the beam strike, depending on whatever we are doing. So yeah, go ahead.
My bad. So when electron strikes the surface of the silicon, those have similarities when using deposition, like scattering around on the surface, or when deposition is you put the one in the top, which is the pure material, and then they kind of spray out the surface.
Right. So you have silicon wave, and then you have done a coating on top of that. The coating is where it strikes, and that coating, now the beam stays where it is. Either you can raster the beam and make the beam go wherever you want to, or you can move the wafer and make that beam make a sketch of whatever device you're making. It's not sketch, but anything like make the pattern of where you want the P of a diode, where you want N of a diode, where you put an electrode line and all kind of things. So that would result into transfer of that design.
Oh, okay.
Then on the right side, we have what you call electron and ion projection lithography. So you can use a beam to write, or you can then flood a big beam and use a kind of a mask like optical lithography. So wherever the electron goes through, they write, they make a projection. So it's a similar thing, but it has its own challenges. With electron beam, there's another thing called ion beam lithography also. So ion beam, instead of using electron, we use ions. Same idea. Instead of electron gun, now we have an ion gun. So we use some material like gallium. When you pump it, gallium ions start emitting out of the material, and you focus it, and now you have very tight ion beam, which you can use to. These are dangerous beams. They are used in a very self-contained, high vacuum, cylindrical things. They are cylindrical up and down. So these people, microscope people, they call them columns. They have a cute word for it. They call them columns within themselves. So that now two things which I'm going to, this is now we are talking about next generation lithography. Remember, we talked about optical lithography, and this week we are, one of the learning objective is next generation lithography. So yeah, so electrons and ions, they interact with better. So we coat the surface with a material that would undergo chemical changes when electron or ion, depending whatever system, they whatever they strike with. Right? So, and this is a very similar principle. Then what you call scanning electron microscope. I know we haven't studied scanning electron microscope, but that's in the plans. We will study that. But to just a simple introduction is that, you know, we use microscopes in labs, high school labs, college, right? What kind of, how do we see things in an optical microscope?
Is the reflection of the light?
Light, just light, right? That's why we call them optical microscope. So we shine the light on the sample and we look through with the lens and we see things. When you say electron microscope, what we do is we have the sample and then we shine electrons on it. And we see the electrons that reflect back. And we have a detector through which we see. Now detector, when it gets the reflected electrons back, it creates a picture of what things were there on the surface. That's as simple as that. So we say scanning electron. So of course, the electrons which strike on the sample from a side, they are scanning over the whole surface very fast. And whatever come back, a electron detector would capture the return and create a picture for us. So we don't directly see them, but that's a system which would give us a graphical representation of how electrons have been reflecting back off of a sample. We call it scanning electron microscope. Now, we have electrons, we have electron beams. Instead of looking at reflection, we use that beam to then start making changes on the E-beam resist or that coating that we're talking about. So that's a very, I would say, a 2-minute introduction to electron microscope, but we'll talk more about it in coming module. So when you have these things in place where, now I'm showing you the same thing that I was previously talking about. We have, what are the components? We have an electron gun, right? Which gives a tightly focused electron beam out of it. We use these magnetic coils, electronic coils, to keep it straight and give it velocity to go straight down. And we have then given a pattern generator file, which would now make these coils move whichever direction you want that beam to go, right? So think about it. It's like if you are shooting, Texas is a shooting state, right? So if you're shooting and if you're shooting with an electron beam, yeah, instead of moving your hand, you can put coils around and that can make this beam, your whatever, your aim go right there while you continuously shoot out electrons. Now, 4 years ago, they made, 4 years or 5, 6 years ago, they made Texas campus carry, right? And now everything is online. How things have moved so fast in my life in last 10 years, guys. We are living through some revolutionary period. They allow campus, everybody can bring gun on campus, which is fine. I'm not saying one cannot, but now nobody can come on campus. Think about it. Yeah, so nobody can operate an electron microscope now these days. Think about it. We used to have a kind of a field trip for our class. I feel so bad. Where or maybe some of you have done that. We used to go to, there's a lab in engineering building where they have 2, 3 electron microscopes. Beto, what's the name of that professor? You remember?
XRN, something like that. I always forget the name, to be honest.
Yeah.
I don't know why.
So yeah, we have these things in the engineering building, but unfortunately, we cannot go take a look. Maybe someday. But this is what's a basic fundamental E-beam system would look like, right? So then the word says it's stage. The stage is where you would put your sample and you would then either, in this case, stage or the sample placed here is static and you're moving your beam by these deflection amplifiers, which are getting feed from whatever pattern needs to be generated. Can you guys see my arrows that I'm putting on the slides? All right. You want them to be different color or bigger? Let's put pink here. All right. So, but this all is under high vacuum. And the simple reason for high vacuum is, can somebody tell me why we put them in vacuum?
So the electrons don't interact with the air particles?
Electrons do not interact and go sideways. They stay tightly focused. Exactly. Yes, Krista. And that's number one reason. Number two reason is they, instead of going sideways, they may keep on going straight. They would result, the elastic collision would result loss of energy for them. But so we want to maintain the energy that they have when they strike the E-beam resist. So there are two fundamental reasons. Keep them directionally aligned where we want to send them and maintain the energy that they have when they strike the surface. All right. So typical system runs at 25 kilo electron volts. It's a really high energy system. All right. So questions about E-beam lithography. In principle, it's very much the same as optical lithography, except we are not using a mask. We are writing directly, but everything else, chemicals are different, but the process the same, that you would take the chip, dip in a chemical, it will get washed away, whichever is not exposed or whichever is exposed, depending positive or negative resist. And then we have the pattern written, then we maybe want to do the doping or whatever we do, that comes into the step, right? Now, E-beam lithography has also evolved over years, and there has been continuous push that we want to make smaller and smaller features. What y-axis, what calls it that pixels per shot, that how small can we make and how many can we make in one kind of exposure. But it's always an evolving field. So we'll look at some examples, then we'll look at ion beam lithography. So if you look at the right top picture, that's an amazing image from 2003, which clearly shows that you can make 4 nanometer gap. 4 nanometer is like maybe 10 atoms. That's the kind of gap. So it was a hot field, still a hot field, what we used to call molecular electronics, that can use molecules as electronic functional transistors. I also did some work where we use DNA molecules. The low right image is my countless long nights spent in E-beam on SEM on, what was that, 2006? It says the date there. That I made those structures. I took these images where I made 5, 10, 15 nanometer features. I was working with DNA molecules. So this is what you are seeing is we can make so small features using E-beam lithography. There are advantages, there are disadvantages. Advantages, clear-cut, smaller features. We can have flexibility in design. We can make any type of thing, round, circular, straight. But then the problem is that it's slow because it's a serial process. That being a serial process means low throughput, high cost, defects cannot be rectified because what you have written, you have written. You cannot go back and scratch and make another one. And when you write one layer alignment on the next level is a big headache. But there's some things about E-beam lithography. So today, a lot of industry is using E-beam lithography. Now, talking about ion, it's very much the same principle, but the difference is that electrons are much smaller, ions are much bigger, of course. Ion is an atom which is missing or have been added with few atoms, right? Of course, the size is different. And they can have much, much, much more energy than electrons, right? Because it's a bigger charge atom. And then you have bigger items and smaller items, which can again give you different uh, benefits. So here I've made a sketch where you are using a heavy iron, which when strike the resist would stop very early because it's too fat. But if you have a, I don't know if I should give fat or thin examples, but you know, you get the idea. I'm fat myself. We all are a little bit overweight these days, not doing much exercise. Sorry, I digress here all the time. So if you have small, light ions, they can travel much faster. Swimming, right? Yeah, so swimmers are always very skinny and straight because they have to move fast through this. Now, no different for when you talk about E-beam or ion beam resist, right? So that thing shows us the idea. Now, electron, on the other hand, can penetrate through further, but the problem is that electron can, because of its smile, can go, because of its size, it can go through further, but what it results in, it knocks off secondary atoms, and those secondary atoms can push tertiary atoms, and we end up having a very big feature in resist, what it shows like this balloonish type of features shown here. Do you guys see my mouse cursor also when I move it around? All right,
Yes.
so this is what electron would mean, that the feature will become much bigger before it stops. So they're all challenges in the next generation lithography, that what do you use? For one application, one thing may be better than the other. So here we have, there's some numbers for gallium. The FIB is the tip of that focused ion beam has a temperature of 290 degrees centigrade. So it means that we are restricted in what material can be used, right? I'm talking about if you have polymer or any non-solid material that can have an issue, that if you can use it with there or not, right? So there are then examples of some examples of focused ion beam also. So here they have shown a system where, again, you have an argon ion beam gun. So ions come through. Now ions strike a surface and they have an electron gun. Electron gun is being used to image in real time on what is being written, right? So this is just the setup. Everything else is more on detecting if an ion goes through, and then you have a single line detector. So yeah, technology is there where we can emit one ion and we can detect one ion. Again, under very high vacuum, right? For the same reasons like electron. We don't want it to be deflected and we don't want it to lose its energy. Excuse me. So with focused ion beam, we can remove hard material also, the process what we call as sculpting. So, and on the lower right hand side, what you see is it's an experiment where they have made a nanopore, 1.8 nanometer hole into a membrane, which they ultimately use to detect DNA translocation through. So we have also done some of those things. Right. So now, instead of using one beam, they have also tried what they call as ion projection lithography or electron projection lithography. So you can see instead of a mask, now it is stencil mask. So stencil mask is the same thing what we use to paint maybe on the wall, or what they call screen printing, right? So you have this hard surface, you can spray paint and you remove it, whatever is the design on your screen or your stencil will be transferred on the surface. So that's the kind of approach here. But if you think about it, there's limitation of how much can you make, because if you make the ion beam too spread, you would lose energy. If you lose energy, the ions cannot penetrate deep in your ion beam resist, right? So then that's another issue there. So there are just three ways of how they can be used. You can use them directly, you can flood them, or you can use them into make the image smaller, like a micro copy that we do on copiers. All right, so just few more examples on projecting ions or projecting electrons to write your feature, which may be made on a mask, and then there's you can trans. So okay, now here they are showing lenses, right? And they're making lenses, but they're not actually optical lenses here. They're coils basically. But we understand things better if we make them look like a lens, right? So that's on the projection lithography, right? So this is more again on the talking about the parts or components which I showed you in the previous slide. So you have stencil, which is a mass, which is a thin membrane which holds and design patterns in it. And you cover your wafer with the resist material. You throw ions and they result into making your feature on the surface. So scanning probe. Now this is a slightly different topic. All right, let me ask questions so far. I know it's too much new material in very short period of time, but that's where we can talk about muddiest points afterwards. Yeah, questions?
So I did remember when we see it to the lab to see the electro beam, or my classmates were coding this surface of these items, so the electro beam will be able to see it. I never understand well why they do that using the electro.
Electron beam. What's the
Yeah, they code the surface or whatever they're gonna look at.
E-beam? Okay, so we code the surface with the E-beam resist. We call it resist. So that's the coating which when the E-beam strikes would change the property, and hence you can make you can then make the design of the transistors or design of whatever we are trying to make in the chip.
Oh, okay, because they were.
We call that coating as just resist.
Oh, okay.
Photoresist, basically coming from photoresist. We find a cute name. We just call it resist.
Oh, okay.
So the idea is that this is the coating which will undergo the chemical changes once there is a beam, whether that's electron or ion that will strike to it, and that will change its properties. Right. So that was, so far we have talked about is next generation lithography, where we have a beam and we can translate the idea of the VLSI chip or device by transferring the pattern by projecting the pattern into the resist. Now comes the idea that instead of projecting things, can we scratch the surface and actually draw things with a very, 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 can you see my tip? So on a pen, we have a thick tip, but what if I can make it very, 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 very thin, atomic scale, maybe 5 nanometer, and use it to scratch and write it? We call these, the thin tips, as probes. We call them probes. That's the word we use. Like they send probe in space. It's a machine gone to look for things, look for life, look for gases. We are not taking care of life on this planet already, people around us, but we are sending to look for life elsewhere. Political statement. I don't know why do I do that, but seriously, yeah, we lose power when it rains. And all right, so if you make these tips very small, we call them probes. Now, if I can write it, I call it scanning probe, that I'm scanning on the surface and I'm scratching. Okay, we don't scratch physically, but again, we put a resist, we put a coating, thin coating, and I write in that coating. This is what we call scanning probe lithography. What's the title of this screen? Now, this tip can have many different ways how I can write in a resist. I can put a chemical there and I can write kind of a chemical directly, right? I can put some molecules solution. I can dissolve some molecules and put the molecules on the surface. I can scratch the surface, right? Mechanically, right? I can nano indentation. It's a similar concept like scratching, but the indentation is where you indent something and you go back. Dent something and you come back. Dent something, put the dent and then move, retract and then move, then put a dent, retract. Basically, you retract. You can make the tip to be a heater. So it can generate very, very high heat, and the coating surface can undergo chemical changes because of heat. You can make the coating, which is voltage responsive. You can apply voltage with that. That's what is called voltage biasing, in which you can use this voltage to result into oxidation, or you can just chemically uh, use a material that undergoes chemical changes when it's exposed to electrons, right? Or you can use this thing to put nanostructures and put them in whichever shape you want to put it. Whole bunch of ways how scanning probe microscopy works. But it is same idea. We want to put the features on a chip so we can make nanoscale circuits. This is next generation lithography. All right. Oh man, let's jump into some of these. Not all of these, some of these. AFM. AFM, we haven't talked about AFM yet, but hang on there with me. We'll talk about the basic principle of AFM later on. AFM, simply stating, is a probe tip on a cantilever, on a long, jumping board in swimming pool. Remember, there used to be a thing called swimming pool where you used to go when we were 1 year younger than today. So those jumping board are fixed from one side and free from the other side, right? So if I put a tip here, I can scratch it and it's flexible, right? Goes up and down. And if I put a shiny mirror at the back and put a laser that reflects back from that shiny mirror, and I have 4 photo detectors. Okay, let me take a step back and come again. So think about it. If you have a jumping board, Krista, it's too boring, I know. I'm also feeling young here. Swimming pool, remember that thing? Jumping board. Okay, we have lizard, and I have LGM327. Who's that? I have 6 people in this room. I have Lizard, who has not turned her video on, and I have another student called LGM327.
Ruby, he's talking to you.
Oh, no, but what's the name? LGM327.
Her name's Ruby.
Who?
I don't know if you can hear me.
Yeah, I can hear you now, but I don't know your name.
Yes, Ruby Robles.
Oh, Ruby, okay. I don't know, you didn't change your name, so.
Yes, it's because I'm using my phone this time. Last time I was using my laptop.
I'll change it for you. I just did that.
Excuse me?
I just changed your name.
Oh, okay.
Because when I'm talking, I need to know who am I talking to.
Yeah, sorry. It's because this is new to me. I usually use my laptop, but right now I'm using my phone for the first time. So this is different.
Don't worry about it. I tell you, I've told my students, if your siblings, kids, pets, husbands, wives, whoever jump at you, don't feel embarrassed. This is new normal. It's okay. It's perfectly fine. Right?
Yes.
Okay. Right. So it's
Okay, thank you.
We all are in it. My wife is yelling at me, and I'm telling her when I mute, and then I come back. So don't worry, we're all doing this.
Okay.
It's perfectly fine.
Okay, thank you.
Sometimes, so just keep it down. I'm talking and recording a lecture, so it's okay. All right, let's get back to swimming pool. The thing used to be swimming pool. So that's the jumping board. That's what we call a cantilever in engineering. At the cantilever, end of the cantilever, the loose end, we put a very fine tip, right? Now, at the top of cantilever, at the edge, I put a mirror, very fine mirror, very shiny mirror. And I put a laser which points at that mirror. And of course, it will reflect back, right? It will go somewhere. Where it reflects back, I put 4 photodetectors. Now, if the cantilever goes up and down, my photodetector will measure that change that it is going up and down, right? So I can, and now if I start moving this on the surface of a material, on the surface of a chip, as soon as there is a feature, it's going to go up. My photodetector is going to figure out, find out there is a nanoscale object on the surface because of which this thing went up and down. That's your atomic force microscope, because that tip is so sensitive, which is coming out of this board. It will move when it encounters a nanoscale feature on the surface. And we don't have just 4 photodetectors. We have a bunch of photodetectors that are continuously measuring this reflected laser beam, which is very fine, very small, thin. So very small change from this movement will be recorded. Now my computer knows Z change and my computer knows XY change. What stage were we looking at when this deflection happened? That's AFM. I can use that same tip to write and scratch things at the surface, which is this slide that we use AFM to write. They have done at Northwestern. They've been doing lots of work in Northwestern University. They put molecules on the surface with that. So they would dip that tip somewhere. That's the next slide. Just wait for that. Or they would magnetically change an atom. That's the right-hand side, top side. Or they would chemically have some reaction from the tip and the material on the surface. Or they can mechanically scratch a surface. These are all different ways of how we do that. The problem is that the feature size depends on the tip size. So the smaller the tip. So yeah, we are restricted on how small can we make. It's restricted on how small can we, how quickly can we, what's the word? How tightly packed can we write something, which is the pitch thing here written. Pitch goes down. Its reliability. Sorry, we can make smaller things depending on the size of the tip. We can just pick the tip and very next to it, write another line very close to each other. But problem again is it's a serial process, low throughput. Now, talking about that tip, this red thing is on the left side is you have a chemical, you dipped it in water, just like you remember they used to have those feather pens. You dip in the ink and then you write, right? As long as the ink is there on the tip, you write, then it dries up, you dip it again, right? 200 years ago, 150 years ago, that was those feather pens. That's a similar idea. We take the tip, dip it in chemical, and we write it. Just a cartoon showing the same thing, right? So now they call it dip pen lithography. Instead of just dipping it over and over, they have come up with very, very interesting ways where they make some reservoir on the top, where they fill it with the ink and ink being the chemical. That can be anything. There's a whole bunch of lists they have shown they can write. They can use molecules, DNA, proteins, peptides. The problem is still the throughput. You cannot write too fast. Another example, now here on the right side is shown that if you make things move too fast, which is that yes, moving too fast, you're gonna make line very, very, very thin. That becomes an issue because now you would not have enough chemical to make any change there. So throughput versus the feature size is an issue, right? So couple of more slides and we can stop for today. Another example where they, instead of using one tip, they made many tips and they flipped it and they used those tips to write the features across the whole bigger area, parallel writing with thousands of tips, right? Oxidation, so your tip can result into oxidation, introducing oxygen species at the surface by heating, by reaction, whatever reason, by voltage, right? Depending on whatever is the reactivity there. So let's start with AFM lithography, where we can use polymers to write. We can a whole bunch of things. So this is a very interesting picture on the right-hand side. We look at scale bar, 120 nanometers on the right side. So this is very, very high resolution feature that they have made at that scale. All right, question. All right, so again, to sum up about the next generation lithography, we understand what is optical lithography. We have to put the design from the VLSI layout to actually on the chip surface. But we can only do so much with the wavelengths that we have in the UV. So we are looking for how smaller features can be made so we can make many more nanoscale features. That's what we call next generation lithography. Now on the course management for KPR, I have, it took me a while to get to my computer to extend the deadline. Now you know your deadline for the KPR presentations also, which is Sunday, and you have to comment on each other's KPR also. Some X number of time I have written there in the Blackboard. And yeah, I'll be putting out the soft chalk also in next couple of days. We are just trying to catch up with the delay because of the hurricane. So, but we are still on schedule to do everything that we were planned to do in the course, right?
So about the KPR recording, do you have specific things that we need to cover? Like, do you?
It's 10 minutes. You can do exactly what I do, which is I use Zoom to record a lecture alone. And then, you know, I get the video, it gives me a local video. And in that Zoom, I have my PowerPoint presentation, right, which is shown. And I'm just in a corner. That's what you can do. You can upload the 10-minute on YouTube and share the link, or you can share the video directly in discussion board.
Okay.
You have to talk about that KPR, that what's special about it. And for 10 minutes, I say you want to make maybe 8, 9 slides. That's perfectly fine. Right?
So it doesn't, you don't have specific things that you want answered or questions that you want answered?
No, the criteria for KPR was given that you have to tell us why do you think, number of citations, you have to give maybe, I think there were 2 examples of its impact, 2 examples.
Yeah.
And
so exactly like the paper?
Exactly like the paper. It's just an expanded version of that paper where we like to hear you, how convincing you are about that.
Okay.
Right? Yep. All right. For the group research proposal for team building, maybe some of you already know each other, but I'll be making a discussion board to maybe post your short resume there so each other can see who we feel comfortable with each other and form the teams. I know it's not a perfect way of forming teams because we cannot meet each other. We don't know each other's background. But that's the best we can do about each other, that what are your strengths, weaknesses, and all that. But that's also coming up very soon, where I need to see the team forms for you for your group work. Right?
Okay.
Questions? All right. If not, then I'll let you go. Thanks for adjusting your schedule with me on Friday. And I'll see you guys soon on Blackboard. Bye. Take care.
See you. Bye.
Bye-bye.